So in sub-exercise 2, we are looking in a more advanced model of negative externalities. In that we will consider a tradable permit model where, yeah, I think you should have seen the slides by now. On the lecture slide, like you should have seen information on this on the lecture slides, or if not, you will see it next week. But nevertheless, we will cover the exercise this week. So in the tradable permit model developed in the lecture with identical firms and the possibility to reduce pollution, show that the government can achieve efficiency, so social efficiency, by either imposing a tax, so described by this equation here, on emissions or providing each firm with a permit to emit at most rho units of pollution, where rho is described by this equation here. Yeah, and I will describe what those expressions mean in a second when we deal with the exercise. So due to the sake of time, I will only consider the case where we have a tax. So I will just consider this here. So the situation here, for the case where you have kind of a upper limit on the upper limit on the emission, please have a look into the PDF, into the solution PDF. There I provide the solution also for this case. Yeah, but here we will care only about, at least in the video, we will only care about the situation where the government wants to achieve efficiency by using a tax. So yeah, let's dig into the model. And yeah, start with notation as usual. So we have n identical consumers, which means that they're homogeneous. So no heterogeneity in preferences. So n identical consumers. And they have utility. Each of them has a utility function given by z plus phi x minus d, or function d evaluated at e. So let's go through each of the components. Z denotes consumption of the numeraire good. Consumption of numeraire. X is the consumption of some other good. Okay, so we don't specify what it is. And we impose the following structure on this utility of the other good, in that we assume that the marginal utility is strictly positive and the utility function for the other good is strictly concave. And in addition, if you consume 0 units of the other good, your utility from this other good will also be 0. Capital E denotes the amount of pollution. So the total amount of pollution, basically. And the function D, is this utility. This utility from pollution. And we have the following assumptions on this D function. So it's strictly increasing. It is strictly convex. And if there is no pollution, the utility or the disutility from pollution will also be 0. Okay, and this summarizes everything with respect to the preferences of the n-identical consumers. So they have this quasi-linear utility function here, which can kind of describe situations where you have some numeraire good. It could be money, for instance, or anything else, and you have utility from some other good, and there is pollution in this model. So we have some further assumption. So good X is produced by capital, or not capital, but M competitive firms. And each unit of X which is produced causes gamma A units of pollution. Where A denotes pollution reduction effort. So if you think about it, it could be a situation where X is kind of let's say X is for instance steel, very simple example that we had before. So X is steel and it causes pollution, and the firms can invest into technology. So the investment is captured here in the model by A, and this technology has the consequence that it reduces the pollution which is caused by each unit of X produced. And the reason for this is because there is kind of, we impose structure with respect to this gamma function. So we say that gamma is strictly increasing in A and that it's strictly convex. So did I say strictly increasing? I meant strictly decreasing in A and strictly convex in A. And if you choose, or if there is zero kind of zero pollution reduction effort, then we simply set this gamma function equal to some gamma which is strictly larger than 0. Okay, and this will be kind of the pollution of a firm when it is not investing in any type of pollution reduction. And as I said before, you can see A as kind of an investment into pollution reduction technology. And the higher the effort is, the lower will be the amount of pollution due to production of this good X. And we have some further notation. So the unit production costs of X are C plus eta times A, where eta is strictly larger than 0. Yes, so what you can see here is that um, the firms have some kind of a base cost C, which is kind of the production cost of a firm when it is not investing into pollution reduction at all. And the higher the pollution reduction effort that a firm is kind of choosing, the higher will be the marginal the production costs of good X. Yeah, so by this, the firm is kind of internalizing that if it is reducing pollution, it will have higher costs. Yep, so there is a kind of a trade-off there in this model here. So this finishes the notation for the model. So I know it's quite a lot, but I think we covered everything. There is one more thing that I forgot. I just looked into the solutions. So there is y. So there is the parameter y, and this parameter denotes the endowment. Endowment of the numeraire good. Okay, so this is kind of the money or the wealth that each of the consumers in the model has. And yeah, let me just check 1 second whether I covered everything. And I think, yes, I covered everything. So what we will do now is we will proceed in 3 steps. So in step number 1, I will kind of solve an optimization problem in this economy from the perspective of a social planner, okay, who's trying to reach the social optimum. Next, I will consider a market equilibrium, a market solution where we do not have a social planner and where the agents in this market are optimizing by themselves. And third, I will consider the situation where the government is imposing a tax. So a tax which was given in the exercise description of exercise 2. And then we will look at the market solution again when there is a tax as given in the exercise description. And we will simply compare the different amounts of pollution in those 3 frameworks. And that's the plan for this exercise. So let us start with the social planner. Social planner. So capital Z denotes the aggregate consumption of numeraire, and capital X denotes the aggregate consumption of the other good. So now, using this notation, the optimization problem is, so the optimization problem of the social planner is given by the following. So the social planner is maximizing over aggregate consumption of the other good, aggregate consumption of the numeraire, and the pollution, or the amount of pollution reducing effort. And it's maximizing the social welfare function, which I here denote by V. So V depends on capital X, Z, and A. And yeah, how does it look like? So we're maximizing the average consumption. So since all the consumers in this model are heterogeneous, we can simply, so instead of considering one kind of particular amount of the numeraire good which is consumed, we consider the average amount of numeraire consumption in the economy. This is then denoted by capital Z, which is the aggregate amount divided by the amount of consumers in the economy. So to this we add the utility of the other good evaluated at the average consumption level of the other good. And from this we subtract this utility of pollution evaluated at gamma A times capital X. Yeah, and keep in mind that we do not divide capital X here by n because for pollution, the total amount of capital X produced is used or is evaluated for each of the consumers individually. Yeah, so this is the idea of the negative externality. And the government or the social planner is maximizing this objective function such that the following constraint is fulfilled. So average consumption of the numeraire good is or should be equal to the average endowment, which is then simply y because everybody has the same endowment, minus the production costs of the other good, so which was C plus eta times A times the average consumption of the other good. Okay, and this is the optimization problem. And I will, numerate the equations here so we can then always refer to them, or I can always refer to them and you know what I'm doing. The enumeration here will be different than the enumeration of the solution PDF, but I will be consistent in this video here. And also in the PDF, so in the solution PDF, it will be also consistent. Okay. So the first thing is we rearrange the constraint given by equation 2. So rearrange 2 in that we end up with, I made a mistake. I'm sorry, I think I made a mistake here. Yes, the mistake that I made was that I already took the rearranged. I already took the rearranged version of the constraint. So this is the rearranged version. Let me just write down again the correct or the kind of the more intuitive budget constraint in this economy without rearranging it. So what I wanted to write down before when I was talking about the constraint is that the total amount or consumption of the numeraire good in this economy plus the production cost, so the total production cost of the other good should be equal to the total endowment in this economy. Yeah, so this is a more intuitive way to write down the constraint. And if we rearrange this by dividing by the amount of consumers in the economy, then we get this rearranged kind of budget constraint. And I did this because what I will do next is I will plug in for the average consumption of the consumers with respect to the numeraire good, and I'll plug this into the objective function for the corresponding expression here. And yes, by doing this, so plugging in, plugging in for Z divided by, or capital, should be a little larger, capital N, Z divided by N in equation number 1 gives us the following. So now we got rid of this capital Z. Now we only have the following maximization problem: max over capital X and A and we maximize w x of a. So I just kind of reformulated the objective function or changed the notation. And now we maximize y minus c plus eta times a times capital X divided by n plus phi of capital X divided by n minus d, so the pollution, evaluated at, the total amount, or this utility of pollution evaluated at the total amount of pollution in the economy. And this is basically the, a simplified version of the optimization problem, which then only depends on two endogenous variables, namely the aggregate amount of the other good which is produced and the effort of pollution. So let us consider the first order conditions. So if we maximize the welfare function, or take the derivative of the welfare function with respect to capital X, what we get is minus 1 divided by n times c plus eta times a plus 1 divided by n multiplied with phi prime capital X divided by n minus gamma a times d prime of gamma a times capital X, and this should be equal to 0. And if you rearrange this, what we get is that phi prime of x, capital X divided by n is equal to c plus eta times a plus n times gamma a times d prime gamma. Let me just go a little bit on the right with this here because I will need the space. D prime gamma a times capital X. And this should be equal to 0. I'll need to go a little bit more to the left because I will label this first order condition here, which I rearranged by equation number 3. This will be important. Second, if we take the first order condition of the welfare function with respect to the pollution reduction effort A, what we get is minus capital X divided by n times eta minus gamma prime a times capital X times d prime of gamma a plus, not plus, sorry, multiplied with capital X. And this should be equal to 0. And if you rearrange this, we end up with eta being equal to minus n times gamma prime a times d prime gamma a times capital X. And this equation will be denoted by equation number 4. And equation number 3 and equation number 4 are describing the social optimum values of the total amount of consumption for the other good, so for X, and the socially efficient amount of pollution reduction. So in order to denote this tuple, so this tuple consisting of capital X and A, I will denote the solution of those two equations by the following. So solution is capital X E and A E. So we can write this into the first order conditions, which are rearranged in the following way. So you simply put an E over each of the A's and over each of the capital X's, just for the rearranged um, equations. So the tuple capital XE and AE is basically describing the social efficient amount of pollution and production of capital of the other good. And what are those two equations describing? So the first equation, which you see here, is basically saying that oh, sorry, there is there is 1 0 too much here. So this then is not equal to 0 anymore. Sorry. So this equation here is saying nothing different than the marginal utility of capital X of the other good should be equal to the production cost, okay, which is then captured by C plus the factor capturing that pollution reduction effort increases the costs here. So the total costs of producing a marginal unit of the other good is captured by this part here. And this part here is capturing the negative externality which is caused on each of the consumers when producing a marginal unit of the other good. So you have n here, so it happens n times because the externality is imposed on all consumers. And what do we have? So what is imposed on them? So the disutility of a marginal unit which is produced of the other good here. Yeah, so this term is capturing kind of the costs of production of a marginal unit of the other good and the marginal benefit of the other good for each of the consumers on the other side. The second equation here is capturing the marginal benefit of a pollution reduction effort, which is the right hand side here, because if we invest into pollution reduction technology, or the pollution reducing technology, we decrease the negative externality on all consumers. And this is captured by the right hand side here. But on the other hand, we also have costs in that if we invest into pollution reducing technology, we increase the individual costs of production for each of the firms, basically. Yeah. So this is kind of the trade-off that we have. So on the one hand, we reduce the negative externality, but on the other hand, we increase the costs for each of the individual firms. And the optimal amount of pollution reduction effort is described basically by this equation here. And if the two equations, so equation 3 and equation 4, hold simultaneously, then we are we reach the social efficient solution for this model here. Okay, so keep in mind that XE and AE solve equations 3 and 4. Now we will go to the next step. So now we considered the social planner, and now we will go to a situation where we consider a market equilibrium. Okay, so this is situation 2, market equilibrium. So just 1 second. So what can we say about the equilibrium values of pollution reduction and production of the other good and consumption of the numeraire good in a market equilibrium where each of the participants in the market is simply maximizing his own kind of objective function. So what is the first thing that we can see or can say? If, for instance, the firms, when they're producing, when they're thinking about reducing their pollution and thinking about how much to produce, like from with respect to the with good X, so the other good, how much pollution reduction effort are they choosing? Well, what we can immediately say is that the equilibrium amount so equilibrium amount of pollution reduction is A star equal to 0. So why is that? So why is A star equal to 0 the kind of equilibrium of the market, of a market situation? Well, the reason is simply because an increase in A does not have any impact in all on, or it has an impact, but if you just care about your own profit, you do not care about the externality that if you reduce your pollution has, like the reduction of your own pollution has on the other participants of the market. Yeah, and as a consequence of this, basically what you will have is that when you increase the amount of increased investments into pollution reducing technology, what you will do is you will increase your own costs. And by increasing your own costs, you have a competitive disadvantage to other firms which did not reduce their pollution because they can offer the good at a lower price than you without making losses. This is the basic idea. So let's go through kind of the reasoning of why this is the equilibrium amount of pollution if we have a market situation. So suppose, so let me be more precise. So why? Okay, suppose if all firms choose A equal to 0, the competitive price of good X is C. Okay, why is that? Well, if no firm is investing into pollution reduction, then the marginal costs of a unit of good X is given by C. And since we have a competitive, so we have a competitive market, it means that the firms will choose, or the firms will produce such that the marginal costs are equal to, yeah, the marginal revenue, and the marginal revenue here is the competitive price. Yeah, and then the competitive price will be equal to C. So the production cost um, if all firms are choosing kind of pollution reduction effort A equal to 0. Now what we'll do is we will ask ourselves, does any of the firms have an incentive to deviate from a situation where all firms have chosen a pollution reduction of 0? And if this isn't the case, then A equal to 0 is indeed an equilibrium because no firm has an incentive to deviate. So let us first ask ourselves, or let's consider deviation to A strictly larger than 0. So a consequence of this is that price of the firm which deviates, okay, it's important that the price of the firm which deviates changes. Must be weakly larger than C plus eta times A to avoid losses. Because if it would choose a price which is lower than C plus eta times A, then it would sell below its production costs. So it would sell good X lower than its production costs, and hence it would make negative profits or losses. Yeah, and this is kind of, you must set a price which is at least as large as your production or marginal costs in order to make profits. But now comes the problem. But if the price is strictly larger than C, which it is if you choose a strictly positive amount of pollution reduction, then all consumers will buy from the other firms. Since their prices are equal to C. So what you have is that if you as a firm deviate from a situation where all firms, including you, have chosen pollution reduction equal to 0, if you increase your pollution reduction effort, then you increase your own price. But if your price is then higher than the price of the other firms, which are choosing pollution reduction equal to 0, then all consumers will buy from your rivals. And hence you will have no demand. And at the end of the day, you did not generate any revenue. And the consequence of this is that you will not have revenue, but you will have the costs of pollution reduction, which you have as a firm. Yeah, this was the so there was a part in the profit functions of the firm where you were basically being suffering if you invest into pollution reduction. And hence, as a consequence, this cannot be optimal. So this deviation cannot be optimal. So deviating to A strictly larger than 0 cannot be optimal because other firms then can undercut you by choosing a price which is arbitrarily close to C plus eta times A. And then basically what will happen is that each firm will have an incentive to undercut its rival up to a point where all firms are then choosing pollution effort of 0 again, and the prices will be equal to the marginal costs. Okay, so a consequence. So consequence is that A star is equal to 0, and as a consequence, since we are in a competitive market, the equilibrium price will be equal to the marginal costs, which are now equal to C because all firms are choosing pollution reduction equal to 0. Now, we solved the kind of the sub-model for the firms now. Now we're going to the consumers. because the consumers are the ones which generate the demand for the good. So now consider the optimization problem for consumer. So a consumer who does not internalize the negative externality that the demand of this consumer is causing on others. So the consumer is simply considering the following optimization problem. So it's maximizing over the consumption of good X and consumption of the numeraire good. It's maximizing its utility function, which represents the preferences, and the utility function is given by z plus phi x minus d, so this utility from pollution, such that for this individual consumer, his consumption of the numeraire good plus the costs of the consuming, or the price of consuming good X, which is then P, but we solved before for the competitive equilibrium and we showed that the price of good X is equal to C, so the production cost, the marginal cost of the firms. So Z plus C times the amount of good X which is consumed is equal to the endowment of the numeraire good. And we will denote, let me just check up on the numeration. So I had equation number 3 and 4, so we start now with 5. So this will be equation number 5, this will be equation number 6. So we solve 6 for Z and plug into 5. So for Z, we solve the constraint for Z and plug into the corresponding value of C in equation number 4 on the objective function. And then if we, what we get is maximize over X. And we maximize the following. So we maximize U equal to, so what do we have now? Y minus C times X plus phi of X minus D of E. And if we take the first order condition here, what we get is phi prime of X. So the marginal utility of the of good X is equal to the marginal costs of good X, which is then equal to C. And now, since all consumers are identical, what we have is that X star is equal to, this looks ugly. So X star is equal to capital X star divided by N. And hence, what we have is that the margin utility of average consumption, so capital X star divided by N, is equal to C. And we denote this equation here by equation number 7. And what we wanted to do is that we wanted to compare the kind of different amount of pollution which are caused in the amount of pollution what we wanted to do is we wanted to compare the pollution reduction effort and the amount of consumption for good X in the two different frameworks. So the first one was the social planner framework, and here we have the competitive equilibrium framework. So obviously what we had first shown is that, so comparing comparing to social optimum, the first thing that we showed is that A star equal to 0 is smaller than A. I think we denoted it by E, if I'm not mistaken. Just 1 second. 1 second, please. Yes, we denoted the solution of the social planner problem by XE, so capital XE and AE. And obviously, since A star is equal to 0, it's strictly lower than AE, which is the pollution reduction effort in the social optimum. So compared to the social optimum, there is less pollution reduction effort in the competitive equilibrium. So this will be kind of observation 1. And observation 2 is that X star will be, so capital X star will be strictly larger than XE. So there will be too much consumption of good X. And the reason is simply if you take a close look on the condition which defines aggregate consumption of good X in the competitive equilibrium, what you see is that the marginal utility of average consumption of good X is equal to the production costs of good X. So this is the competitive solution. And if we go back to equation number 3, what you see is that in the social optimum, on the other hand, the marginal utility of average consumption of good E of good X is equal to the production cost, but including the pollution reduction effort, so the total costs, and including the negative externality which is caused on all individuals. There should be, this is also something that I forgot, there should be an E here. So capital XE is always lower than X star because we also consider the increased amount of costs due to pollution reduction effort, and we include the negative externality that a production of the good X is imposing on all the other consumers, and hence this will imply that we will produce more of the good X in a framework where we have a competitive equilibrium. And this finishes the comparison of the social optimum to a market equilibrium solution. So to finish this exercise, we were given kind of a hint in the exercise description. So what we wanted to do is that we wanted to show that the government can impose some kind of a tax to achieve efficiency. Okay, so let me just see how I denoted this here. This is market equilibrium. So now in case 3, we will consider market equilibrium. Market equilibrium plus taxes. Okay, so now the government imposes tax, so some kind of a tax, which is described by T equal to the amount of consumers times the marginal disutility of pollution in the social optimum, so AE times capital XE. So it's not just a tax, it is, to be more precise, it is a unit tax or pollution unit tax. And what we want to show now is that if the government is doing this, so this is on the side of the firms, what we want to show is that now if all the individuals in the market are kind of maximizing by themselves their objective functions, even then a consequence will be, when we consider the taxes, that we reach the social efficient amount of pollution reduction. and aggregate production and consumption of the of good X. So by having this pollution unit tax, what the government is basically doing is that it's affecting the marginal costs of production for each of the firms. Okay, and how does it look like? So since we are in a competitive equilibrium, in a competitive market, the price will always be equal to the marginal costs in the economy. But now there will be a crucial difference in that what we'll consider now is that now the price of the firms will depend on the pollution reduction effort, obviously. So why is that? So the cost is always C plus eta times A. This was what we had before, but now there is a slight change. Now we have this unit pollution tax. So for each unit of pollution which is captured by gamma times, so gamma depending on A, the firm has to pay N times the marginal disutility from pollution in the social optimum. And basically the right-hand side is describing the true kind of marginal costs in this economy of producing a unit of X, which due to the tax incorporates the negative externality on the consumers in the economy. And what the firms now want to do, so now please keep in mind that this price depends on A. So the firms want to choose an amount of the pollution, also a pollution reduction effort, such that the price is minimized. Because only when choosing the minimum price, they can ensure that they will have strictly positive demand because all consumers will buy from them. And only by doing this, they can ensure that they make non-negative profits. Okay? So firms choose A to minimize market price. Because if they do not do this, they will end up with pollution reduction which is too high, and other firms can choose a lower pollution reduction effort, and hence the firm which has a pollution reduction which is too high will make negative profits. Yeah, it will make losses because it will not generate any demand for it, and hence it will end up with losses. So now all the firms need to minimize the market price. So the optimization problem is minimize over A. So what are we minimizing? We're minimizing the market price, which is equal to C plus eta times A plus gamma A times N times marginal disutility gamma AE times capital XE. So let's have a look on this on the first order conditions here. So we will consider the first derivative of the price with respect to pollution reduction effort, and this gives us eta plus gamma prime A times N times D prime gamma AE times capital XE. This is supposed to be equal to 0. And if we rearrange this, what we get is that eta is equal to minus gamma prime A star times N times D prime of gamma AE times capital XE. So this is a necessary condition for a minimum of the price, which we will denote by, let me go back to my numeration. So this will be equation number 8. Now, of course, we do not know whether the solution that we found here, so this A star, is indeed a minimum. In order to find out about this, what we do is we take the second derivative of the price with respect to pollution reduction, and then we get gamma prime prime A times N times D prime of gamma AE times capital XE. And due to our assumptions with respect to the gamma function and the D function, this is strictly positive, and hence the solution that we find in equation number 8 is indeed a minimum. Now, if you look, the solution A star in equation 8 is equivalent to solution of, and now let's go back to the second first order condition in the social optimum, which was given by this here. And now if you take a close look, you can see that the equations, so the first order conditions here, look quite similar, and that if we set xe star, if we say A star equal to AE, we end up with exactly this kind of solution here, which describes the amount of pollution reduction in the social optimum. Okay, so the tax may indeed make sure, due to the competitive structure of the economy, of the market, where firms are trying to undercut the prices. So it makes sure that when we have the tax, which is then equal to this expression here, that firms choose a pollution reduction effort which is equal to the social efficient amount of pollution, AE. Yeah, so the solution is equivalent to the solution in equation number 4. In 4, therefore, pollution reduction which fulfills 8 is socially efficient. So by imposing this tax, we made sure that, the firms are choosing pollution reduction, which is socially efficient. Okay, now we need to look into what the consumers are doing given the optimal amount of pollution now, so AE, when they are maximizing their individual utilities without directly internalizing the negative externality that their demand is causing on other consumers. So given A star equal to AE and the resulting market price, the optimization problem of a consumer is the following. So the consumer is maximizing over X and Z. So now in small caption, it's maximizing its utility equal to Z plus phi of X minus the disutility from pollution, such that Z plus the price of good X, which is now, if we consider A star being equal to AE, is given by the following. So it's C plus eta times AE plus gamma AE times N times the marginal disutility from total pollution. Okay, I need some space here. This times, so this is the price of the of good X, and this should be equal to Y. So solving this constraint for Z, so Z here, and plugging in for Z into the objective function gives us, and then I shortcut some of the steps. So if you do this, you end up with an optimization problem which only depends on X, and then you can take the first order or the first derivative with respect to X. What you get is that, so if we take the derivative with respect to X, we get the following. So we get the marginal utility at X minus C minus eta times AE minus gamma AE times N times D prime gamma AE times capital XE. This should be equal to 0. And if we solve this or rearrange this, what we end up with is psi prime of X is equal to C plus eta times AE plus gamma AE times N times D prime of gamma AE times XE. So this is kind of the condition that we get. So this is the first order condition, and since all the individuals are again identical, so they're homogeneous, what we get finally is, so since consumers are identical, we can simply say that X star, so small x star, is equal to capital X star divided by N, and hence what we have is the following condition. So capital X star divided by N is equal to C plus eta times AE plus gamma AE times N times the marginal disutility of pollution, aggregate pollution, at the social optimum. And this here will be equation number 9. And if you take a close look, the X star which solves this equation here, so choosing X star such that this equation here holds, will basically represent the first order condition that we had for the social planner with respect to the marginal increase of good X. So X star, which solves equation number 9, oh, the other way around. Equation number 9 is given by XE in, let me just check the numeration. I think it was equation number 3. Yes, it's exactly the XE which solves this equation here, so this first order condition here. And as a consequence, the amount of capital X star, which is demanded here, will be equal to XE. And then, oh, sorry, I just forgot. I forgot again with the number. So this is equation number 3. So in 3, and the consequence will be that not only with respect to the pollution reduction, when we're considering a tax, the pollution reduction in the competitive equilibrium with a tax will be equal to the social efficient amount, but also X star, so the total amount of good X in the competitive equilibrium with a tax will be equal to the socially efficient amount of, the social efficient demand of good X in the social optimum. Okay, so a consequence is that X star and A star are equal to XE and AE. Yeah, so if the government is imposing this type of a tax, a consequence will be that the the amounts of good X demanded by the consumers in a competitive equilibrium and the pollution reduction chosen by firms in a competitive equilibrium are equal to the social efficient amounts. And this finishes this sub exercise, and with this also what we covered from this problem set. So as I told you before, due to sake of time, I did not cover kind of the upper limit on pollution, which the government can also impose in order to reach efficiency. But if you want to see this, just look into the PDF. There I wrote down the derivations for this case. And otherwise, then see you next week, where we will probably talk about the Coase paper and some other papers on negative externalities. See you next week.